We have introduced the continuum approximation method. From now, we just call it CA. So the CA method can be used to solve the time-varying problem. There are actually many interesting insights we will discuss now. Recall that when we have the constant demand problem, so we want to minimize our total cost, and then this gives us the optimum solution for the headway. Now for a time-varying demand, our CA method, we will minimize, and then this gives us our optimum headway function in this expression. So you can compare the cases for the constant demand and for the cases where we have the CA. Actually, the only difference is that our CA solution just adds a time dimension for the input demand rate in the constant demand rate case. So in other words, our CA solution has its corresponding constant demand solution when we set at specific time of t our demand rate is constant. So in the figure, that means at any point, we call it this is a neighborhood. So we assume that for a neighborhood nearby a specific point, we can estimate the time-varying problem by a constant demand problem. So sometimes when we consider the demand rate is constant, so that means the demand rate over time is a constant. So we call this case a homogeneous problem. And typically, we do not have a specific boundary on the time dimension, so we may call it infinite planning horizon homogeneous problem. So as we can see, this one gave us our optimum solution analytically. Because of the symmetric properties, the problem can be easily solved. And then actually when we solve a general time-varying problem, actually our demand rate can have some changes over time, but still we can assume it to be slow varying if that is the case. That means it is not like very zigzag. So under the slow varying assumption, we can solve the problem piecewisely by the homogeneous problem solution. That is our physical meaning for our CA solution. So that means for a specific time nearby, we approximate this time-varying problem, or we call this heterogeneous problem. We can estimate this heterogeneous problem by a piecewisely homogeneous problem, assuming that the parameters, for example, at time t, the parameters at time t, for example, the demand rate at time t. Let's assume the problem is a homogeneous problem where the demand is a constant demand rate over the entire planning horizon, which is infinite homogeneous problem. And then we solve this problem using our analytical solution, and then use this analytical solution to estimate the local optimum headway. So this is the first insight. Now let's see the second insight. In general, our time-varying problem, we want to determine the dispatch schedule. So the dispatch schedule is somewhat discrete. We have multiple time points where we need to determine when we dispatch the truck. So this is somewhat discrete. And then remember, we solve this problem by either shooting method or by dynamic programming. So we can have a solution. Let's see, T0, T1, Tn, or somewhat we put Tmax in the end. So that's our somewhat discrete solution we want to obtain. So the solution process, typically we can use dynamic programming or shooting method. And then what CA method is doing, we just first reformulate the decision problem into its equivalent continuous version. So here, remember this HST indicates a headway. This headway is a piecewise headway given by T0, T1, Tn, and so on. So this is the exact reformulation. And then after we do the reformulation, we do our approximation. So that gives us a totally continuous problem. So we estimate the decision headway by a decision function. See, previously our decision is t0, t1, blah, 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 the schedule where the headway exactly capture the schedule. But now we approximate this headway, piecewise headway function by a general continuous function or a functional across the planning horizon, ht. And then we decompose the problem into a piecewise homogeneous problem by just optimize the integrand. So using CA, we calculate the optimum solution of optimum headway at each time point independently. And then later on, we convert our continuous solution back to the discrete solution. For example, we use our 45-degree method. So this tells us how our CA works. So our CA actually formulates the problem into its continuous version and then solve the problem using analytical method, or takes the derivative or calculates optimum functional and then gets the continuous solution. And finally, we convert the continuous solution back to the discrete solution. So here, let's see, we have the reformulation. So this is our original problem, call it original problem. So we need to find the optimum headway or the schedule, which is relatively difficult. And then we have our CA, which approximates this function. Our decision is changed. So that means when we solve the optimum solution, we can get, remember our solution is, so we plug this in. After some simple derivation, we can get this expression. So if we can solve the optimum solution for a general problem, then we can denote this to be our true optimum total cost. And then our CA solution actually gave us a very good estimation because the integrand is relatively easy to calculate. So the integrand, physical meaning of this integrand is estimated total cost per time. And also remember, we can estimate optimum headway. And then we know that the inverse of the headway, this is a shipment frequency or the number of shipments. So in this end, we can estimate the number of shipment from T0 to Tmax just by inverse of HT in this specific case. So after we obtain the analytical expression of our CA solution with the number of shipments, actually we can still apply our sensitivity analysis to the problem. For example, let's see, what about CF increases? So same as the basic one-to-one system where the demand is constant, we can see when the fixed cost increases, the total cost increases in the square root order. And then when CF increases, the number of shipments reduces in the inverse of square root order. Similar analysis can be done for CI and then D prime. So that is the benefit for this analytical solution. So then in case you can analyze sensitivity for a general heterogeneous problem.